So deep learning has made amazing progress in the last few years and decades. And some people think that it might be enough to take what we have and just grow the size of the data sets, the model sizes, computer speed, just get a bigger brain. So the classical framework for machine learning is based on the hypothesis of IID, independently and identically distributed data. Now, unfortunately, this assumption is too strong. In reality, is not like this. Most of the data we get isn't IID, and so in practice, what many people do, when they collect data, they shuffle it. Now, the IID hypothesis was good, but if we discard it, we need to replace it by something else. So systematic generalization, really, it's about the idea that we can get that by dynamically recombining existing concepts. Unfortunately, current neural net architectures are not that good. There are combinations of the linguistic concepts that are present in the questions that just don't come up in the way that the data is generated. And the current methods, when you ask them to answer these kinds of questions, fail completely, whereas the human wouldn't even realize that these combinations are not present in the data. We want to keep the power of generalization of the distributed representations. We want to make sure that the kind of search that is involved in things like reasoning and planning can be done efficiently. And finally, we need to make sure we build systems that can properly handle uncertainty in the world, and that includes being able to manipulate variables, things that don't seem natural in the neural net world, but as I'll try to convince you, we now have actually built the tools for doing that in deep learning using attention mechanisms. Attention is about doing computation in a focused way. So in a way, attention is parallel, right? We're considering all the possible elements in some set, and we're computing a score for each of them in order to decide on which one or which ones we're going to put attention. Now we have these systems of operating on sets. Why is it a set? Because the attention mechanism doesn't care of the order in which we're putting these elements in the first layer. It just picks one according to how well it matches some kind of learned policy. But the information about the relative position of these elements say in your brain or in a neural net architecture doesn't matter anymore. So now we're at the part of my presentation when I'm going to talk about the kinds of priors, the kind of structures, the kind of assumptions and regularization that we could use in order to encourage our learning systems to do a good job at out-of-distribution generalization and the kind of conscious processing abilities that I've been talking about. Think about the kind of statements we can make with natural language. Like when I say, if I drop the ball, it will fall on the ground. Now, this is a very powerful statement because it's true with high probability, and yet it involves very few variables. So the fact that it uses very few words means that the relationships that are being described can tightly capture some element of the joint probability through very few variables at a time. Now, this is different from the usual assumption that you find in many papers these days that study high-level representations that are supposed to be where the variables are supposed to be independent of each other. This so-called disentangling work, which I think is a misunderstanding of the goals of deep learning, which was to learn these high-level representations. And so instead of thinking of these variables as completely independent at the top level, we think of them as having this very, very structured joint distribution. What I'm saying is, instead of imposing the very strong prior of complete marginal independence at the high level, we can have this slightly weaker prior, but still very strong prior, that the joint is represented by a sparse factor graph. So next, I want to talk about the meta-learning aspect and another hypothesis that's important to deal with how the world changes. So meta-learning is something really hot and cool these days, but actually started several decades ago. And what it's about really is about having multiple timescales of learning or multiple timescales of iterative optimization like computation. So typically you would have an inner loop like normal learning and an outer loop like evolution, which optimizes whatever the inner loop is producing. So the idea is, since out-of-distribution generalization can be obtained if we have the right decomposition of knowledge, we can use out-of-distribution performance as a training signal for factorizing knowledge. Okay, the last bit of my presentation is about operating on sets of objects that may be pointable using dynamically recombined modules. So each of these boxes represent a small recurrent net that is updated based on its previous state, but it can also be updated based on the state of other subnetworks. But we are constraining the way that these subnetworks are talking to each other so that it's going to be sparse and it's going to be done in a dynamic way. Also, we use the attention mechanisms to select a subset of the modules that are going to be activated. So this is the idea that there's a bottleneck that dominates the computation. And the other important element is that the things that are communicated between those subnetworks are not the usual standard vectors that we use in recurrent nets. They are these sets of key value pairs. And so what it means is that what these networks are exchanging is, you can think of them as variables along with something like their type. And what we found is that this leads to better out-of-distribution generalization than standard methods that don't use these kind of structures. We've also tested this in reinforcement learning setups where we just replaced LSTMs that were used in a PPO baseline for Atari games and found that it helped on the majority of the Atari games. So to conclude, I think after decades of work on consciousness by cognitive neuroscience, it's time that machine learning looked at these questions and explore the functionalities and the justifications for having these kinds of capabilities. It could benefit, of course, neuroscience because we would be able to provide more detailed account of these functionalities that can then be tested in real people or animals. And it would allow to expand deep learning from system 1 to system 2. So, thank you.